Welcome to The Explainer, where we make complex topics simple. Today, we're diving headfirst into the unsung hero of your local network, the Ethernet frame.
Have you ever really stopped to think about it? When you send an email or stream a video, how does all that digital info travel from your computer to another? Through a real physical cable and show up, well, perfectly.
Welcome to Super Courseva. Unlock the secrets of the internet and master computer networking. Let's dive in.
The answer, as it turns out, is all in the packaging. Okay, so let's break this down. At the most basic level, your information travels in little chunks. The super generic term for one of these is a data packet. It's just a blob of data going from point A to point B. And that's a fine starting point, but things get way more interesting and way more specific than that. See, once that data hits the actual wire, it can't just be a chaotic free-for-all. It needs rules. It gets wrapped up in something much, much smarter, a highly structured container called an Ethernet frame. Now, don't just think of this as a simple box. Oh no. This is more like a sophisticated, high-tech shipping container, complete with an address, special handling instructions, and even its own quality control seal. So for the rest of this explainer, let's think of the Ethernet frame as exactly that, a high-tech digital envelope. And what we're going to do is carefully open it up and look at every single part to see what makes it tick. So we've opened our envelope, and the very first thing we find, it isn't the to address, it isn't the form address, it's not even the letter itself. It's actually a special announcement that something important is on its way. This is the preamble, and its little partner, the start frame delimiter, or SFD. And this two-part system is just brilliant. The first 7 bytes are this really simple, steady pattern of alternating ones and zeros. Think of it like a drum beat, thump, 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 that allows all the network devices to perfectly synchronize their internal clocks. Then, bam, that final byte, the SFD, acts like a starting gun. It basically shouts, okay, everybody, pay attention. The real information starts now. Okay, so the starting gun has fired. The receiver is paying full attention. What's next? Well, now we get to the most basic, most crucial part of any delivery: who sent it and where is it going? This is all handled by something called MAC addresses. First up is the destination MAC address, followed by the source MAC. Each one is a totally unique 48-bit ID that's literally burned into a device's network card from the factory. And my 48 bits, well, that gives us, wait for it, 281 times trillion possible addresses. So yeah, I think it's safe to say we're not going to run out of those anytime soon. It's just like a house on a street. Every device on your local network has its own unique physical address. All right, the frame has arrived at the right machine. We know who it's for, we know who sent it, but what's inside? And more importantly, what is the computer supposed to do with it? That's where the next part comes in, the special instructions. This little section is called the EtherType field. The best way to think about it is like a label on our envelope that says the letter inside is written in Spanish or the contents are a blueprint. It tells the receiving computer's operating system what kind of data is in the payload. Is it an IPv4 packet, an IPv6 packet, something else entirely? This just makes sure the data gets handed off to the right software to be processed correctly. Now, that whole system works perfectly for a simple network. But what if you want to get a little fancier? What if you have one set of physical switches and cables, but you want to create multiple separate virtual networks right on top of it? Like keeping your office phone traffic totally separate from your computer traffic. How do you do that? Well, the solution is a really cool optional piece called the VLAN tag. A VLAN, or virtual LAN tag, gets slipped in right before that EtherType field we just talked about. Think of it like an extra label for an internal mailroom. It tells the network switches, hey, this frame belongs to the phone's network, or this one's for the guest Wi-Fi network. The switches then know to only send this frame to other ports that are part of that same virtual group. It's a really clever way to get powerful network security and organization using the exact same hardware. So, after all the announcements, the addressing, the special instructions, we finally get to the whole reason this frame even exists. We get to the core of it, the precious cargo it's carrying. This is the data payload. This is the actual stuff you're sending. A little piece of a web page, a fragment of an email, you name it. And its size has a very specific range. The biggest it can be is usually 1,500 bytes. That's a standard called the MTU, and it's basically a politeness rule, so one frame doesn't hog the whole network. And the smallest it can be is 46 bytes, just to make sure the frame is big enough to be properly detected. Everything else we've talked about so far is just the fancy packaging to get this data delivered safely. We're at the very end of our frame now. But you could argue that this last little bit is the most ingenious part of the whole shebang. It's a built-in quality control system to make 100% sure our precious cargo wasn't damaged on its trip. It's called the Frame Check Sequence, or FCS for short, and what it is a 4-byte number that acts like a unique mathematical fingerprint for the entire frame. This fingerprint is generated using a really clever algorithm called a cyclical redundancy check, or CRC.
So here's how this works, and it's just brilliant. Before sending anything, the sender runs this CRC calculation on the frame to generate that unique number. It then tacks that number onto the very end as the FCS. When the frame arrives at its destination, the receiver performs the exact same calculation on the data it just got. Then comes the moment of truth. It compares its answer to the FCS number that was attached. If they match perfectly, the data is valid, good to go. But if they don't match, if even one single bit got flipped along the way, the receiver knows the frame is corrupt, and it just throws the whole thing in the trash.
And this is a really, really important point to understand. The Ethernet protocol is smart enough to know if a frame is broken. But, and this is a big but, it has absolutely no way to fix it or ask for a new one. It just discards the bad frame, no questions asked. Think of it like a bouncer at a club. It just knows who to throw out. It's up to a different, higher-level protocol, like TCP, to realize, hey, I'm missing a piece, and then ask for it to be sent again. So when you zoom out and look at the whole thing, you realize this isn't just some random collection of bits. From that initial wake-up call of the preamble, all the way to the final integrity check of the FCS, every single component of an Ethernet frame has a precise and essential job. And together, they create this incredibly reliable and efficient system that moves all our data around. And that really leaves us with a final, kind of mind-blowing thought. We've just dissected one single frame, which might carry just 1,500 bytes of data. Now think about streaming a high-definition movie, which can be billions of bytes. Your computer is receiving, verifying, and perfectly reassembling millions of these little engineered envelopes every single minute. It is a staggering feat of coordination, a silent ballet of data that happens every second of every day.